Hello. Uh, we have done a few lectures on Fourier transform, and today we are going to continue with the same. That is, again we are going to start with Fourier transform only. Do a few questions on it, and let us try to conclude this sort of you can say theory part of the Fourier transform. Okay, so that would be a good thing to do today. And so let us start with Fourier transform. And we've done till now a good amount of properties, and now that we are going to do today something called as like Fourier sine transforms and Fourier cosine transforms. Okay. Fourier sine transforms and cosine transforms. Sine and cosine transforms. Okay, so this is one thing. So for example, what happens is, let's say if your function fx, whose Fourier transform I want to find, let's say it is an odd function. If, let's say, if fx is an odd function, let's say fx is an odd function, then it happens that gk is also an odd function. Gk is also an odd function. What is gk here? Gk is uh, gk is your you can say gk is also an odd function. Gk is here is here the Fourier transform of f of x. So here gk is simply your Fourier transform of f of x. So gk is simply your Fourier transform of f of x. Okay, this is one thing that one must understand. So what happens if your f of x is an odd function? Then your Fourier transform reduces to something called as Fourier sine transform. Okay, and at times these are asked in the examination like direct formula wise, so I don't think there is much to understand here, but just I'm trying to formulate you some theory. So you'll get a Fourier sine transform. That is, if your fx is an odd function, then your Fourier transform reduces to something called as Fourier sine transform. Okay, now let us begin with the theory. So as you're aware that e की power iota theta, yeah, iota you can say kx, this is the kernel of the Fourier transform. This is something that we have already discussed. This is kernel of the Fourier transform. Kernel of the Fourier transform. Okay, and this e की power iota kx can be written as cos kx plus iota sin kx. Okay, this is Euler's formula. This is something that you know from your complex analysis. Similarly, if I want to write what is e की power minus kx, it will be simply cos kx, then it will be minus iota sin kx. I hope it is clear. Okay, now what happens is if I want to find the Fourier transform, let's say it is gk, or you, if you prefer to write the symbol f tilde k, then whichever way it suits you, f tilde k is given by minus infinity to plus infinity. This is f of x, and then you have this e की power minus of iota kx. Okay, this is how you write. Okay, this is how you write. Okay, so this is how you write your Fourier transform. And now uh, let us write uh, let us write uh, the Fourier transform of the same. So let us write the Fourier transform of the same. So let us write the Fourier transform of the same. Okay, now one should understand that e की power minus iota kx contains two terms. Okay, there is one term called as cos kx, another term called as sin kx. Okay, now if you want to integrate from minus infinity to plus infinity f of x e की power minus iota kx, obviously it will contain cos kx term and sin kx term both. So if you take this cos kx term, you know that cos is an even function and fx itself is an odd function. So odd function multiplied with even function will overall give you an even odd function, and this particular integral will go to 0. The only surviving integral here is the sin kx. So if I write my Fourier transform, provided my fx is an odd function, provided my fx is an odd function, then this particular Fourier transform, there will only be one term, that is, and if I write this 1 upon 2 root 2 iota also here, it is like it is at times you'll find that this 1 upon root 2 pi is not there in the definition, but since we have formulated, so I'm writing 1 upon root 2 pi f of x, and then you have the sine kx, and then you have dx. Okay, now you see what is g of k. G of k will be simply minus 1 upon minus iota root over 2 upon pi, and then you have this uh, I can write 0 to infinity. Why? Because I know that f of x is an odd function, sine kx is also an odd function, so multiplication of two odd functions will give you an even function, so 2 will come up, and this from 0 to infinity would give you 2 in front, so you have this root over 2 upon pi. Now you see this will be f of x sine kx dx. Okay, now if whatever I told you in the initial, that if f of x is an odd function, then its Fourier sine trans then its Fourier transform is also an odd function. If you are aware that at the very start I told you this. Now you can see this from the this particular structure also. See, g of k is given by this. Then if I want to write g of minus k, what it would be? So g of minus k would be really equals to iota root over 2 pi 0 to infinity f of minus x, and then you have this f of, sorry, instead of x, now instead of k I have to place minus k now, so I'll get a minus k here, so I'll get sine minus k is minus sine k, so you will get, so, so if you compare both of them, so if you compare both of them, you know that your g of minus k is simply minus of gk. So if your f of x is an odd function, then the Fourier transform is also an odd function. This is something that you should remember. At times it may come directly as a statement. Then Fourier transform is also an odd function. And you would find that only one term is surviving, not cos, but only sine is there. So at times this particular thing is referred to as Fourier sine transform. I'm going to write all these things. Just give me a minute. Then Fourier transform is also an odd function. Is also an odd function. Okay, now you see so I have already written this thing, so I know that my g of k is equals to this, and I know that my f of x is what? My f of x is simply 1 upon root 2 pi. If I write inverse of this thing, so I know that f of x will be 1 upon root 2 pi minus infinity to plus infinity. It would be gk, and I have this e ki power iota kx dk. So if I want to write the inverse Fourier transform, so inverse Fourier transform of gk would give you f of x. Okay, and here instead of dx you would have a dk. I hope it is clear. Or I know that this thing I can expand as, so f of x here I can expand it as, here I can expand it as 1 upon root 2 pi, and here you have this minus infinity to plus infinity. Here I will write g of k, and then e ki power iota kx I will write cos kx plus iota sine kx, and this dk. I hope it is clear. Now you see this is your f of x, right? Now since this is your f of x, and I know that only one of the terms would be surviving. See, because again I know that gk is an odd function. So gk is an odd function, this is an even function, gk is odd function, sine kx is an odd function. So basically what will happen, only this term will survive. So I'll write f of x is nothing but it is equal to iota root over 2 upon pi, and then you have this 0 to infinity, and then you have this g of k, and then you have this sine kx dk. Okay, I hope it is clear. Now, if I substitute in this particular expression f of x, if I want to substitute the value this, I mean this value, so you'll find that this iota would be lost basically. So just I'm writing it here. So if I replace, if f of x is replaced, or you can say if g of k is replaced in f of x, only one thing. So if g of k is replaced in f of x, then the constant factor here will become iota ka square, and then you will have 2 upon pi. So I'm going to explain you, just give me a minute. So basically what I'm trying to convey is, so I'm going to write those two things, then you'll be able to understand what I'm trying to teach. See what is happening. Till now we know that this is my inverse Fourier transform. So my f of x, I know this. And what was g of k? If you remember, g of k was simply minus of iota, and then it was root over 2 upon pi, and then I think it was 0 to infinity, and there was I think simply f of x, and then I had simply sine of kx, and then I had dx. So if I replace this g of k in place of this particular place, okay, this particular place, then what I will get f of x as, so my f of x would then become, okay, then my f of x would become simply like this. So just pay attention here. Okay, so it will become I think 2 upon pi. So this will be minus, sorry, because see there is one minus here as well, and one iota is here, so iota into iota will become minus 1, and this minus 1, so you'll get 2 upon pi. F of x will become this way, and then you have this integration from 0 to infinity. You have this sine kx dk, integration going over I think k, and then you have an integration over x also, so you have an integration over x also. So this is 0 to infinity, and then you have this f of, instead of this variable, I'll use some different variable, otherwise you'll get confused. I'll use f of u sine ku du. Okay, and if I distribute all these 2 pi into two portions, this particular portion is referred to as the Fourier sine transform. This particular portion is referred to as Fourier sine transform. And remember, Fourier sine transform is only possible if your function f of x is an odd function. So this is the structure of Fourier sine transform. So mostly such questions are not asked directly in the examination, but at times you may encounter the formula. Okay, so you just remember that if someone asks you what is the pair of Fourier sine transform, the first thing that you should remember is that the limits are not minus infinity to plus infinity, rather they are 0 to infinity. Okay, and remember this only represents your odd function. The second thing that one must remember is that the Fourier sine transform represents the representation for odd functions. Okay, and I'll write it in this fashion. So I'll write f of s and this x. So basically I'm writing this Fourier, this is simply inverse Fourier sine transform. So this is equals to what? This will be equals to root over 2 upon pi, integration from 0 to infinity. This will be I think gk here, gsk I would write, and then I will write sine kx, and then I will write dk. And if I am supposed to write gsk, then it would be simply root over 2 upon pi, 0 to infinity, f of x sine kx dx. Okay, so this is how it is. Okay, so these are called as Fourier sine transform. Similarly, if you want to formulate the theory for the even function, instead of sine transforms, you will get cosine transforms. So I'm directly writing there. So I'm not deriving that as such. Okay, and also remember that if the f of x is an odd function, then the Fourier transform will also be an odd function. This is something that I've already derived. So similarly, one can write, I would say, Fourier's cosine transforms as well. Cosine transforms. And what are those? So if I want to write f of cx, this will be simply root over 2 upon pi for even functions. Sorry, this is valid only for the even functions. And if I'm writing for even functions, I know that my sine is an odd function, and if sine is odd and fx is even, so if both of them get multiplied from minus infinity to infinity, that integration would give you 0. So only cosine term would remain. So I'll write from 0 to infinity. Here I would get g of ck, and then I will say that this is cos kx, and then you have this tk. I think for exam, I should tell you that only these formulas are important, nothing else. Uh, as such, nothing else is required. So that would give you more than sufficient hint. Okay, at times you may find that this particular constant factor may not be there in the exam, and if it so happens that constant factor is also there and not there in option, then probably there is a mistake in the question, because one has to give this, because some of the books you'll find that they're not writing this normalization constant. A few of the books you'll find that they're writing it, so there is a chance of ambiguity. You need to see these things in exam. Okay, so this is what I would say. Now let us do a few questions that were asked in the examination, so that you will get an idea how to do the questions. And as I told you, I'm going to summarize this chapter today. And if in future, whenever I'll get time or whenever I feel so, I'll do a few more questions on this concept. So today we'll be summarizing this particular chapter. Okay. Now one has to see that that not all functions can be even on the entire domain, that is on entire real line, because you see, whenever you are supposed to find Fourier transform, one needs to see that one would see that the integration, or you can say the transform, is taken from minus infinity to plus infinity. Okay, and it may so happen that your function may not be completely, you can say that defined on the entire domain. Let's say it is only defined for all x greater than 0. Okay, so let's say if I want to find the Fourier transforms, if I want to find Fourier transforms of function which are not defined on the entire real line, but let's say it is defined on x greater than 0, then what to do? Then what to do? Okay. Now in this particular case, we actually define an auxiliary function. In this particular case, we actually define an auxiliary function. Now what is auxiliary function? A function which is defined for all x less than 0. A function which is defined for all x less than 0. Okay, and one has to see that when we find Fourier transform, we need that function may have at most finite number of discontinuities. Okay, it can have only finite number of discontinuities. So basically what is a condition? That if at all I'm defining some auxiliary function, let's say g of x or capital F of x, then this particular auxiliary function can have only finite number of discontinuities, can have only finite number of discontinuities. I'll give you an example and make you understand, don't worry. Finite number of discontinuities. Okay. Okay, and let's say there are two ways of choosing this auxiliary function. There are two ways of choosing this auxiliary function. What I can do is, see, if my function is defined for all x greater than 0, that is f of x is defined for all x greater than 0, now there is an issue with x less than 0. Now there are two ways. One can write this particular auxiliary function capital Fx as simply f of x for all x less than 0 also. Okay, sorry, f of minus x for all x less than 0. If I want to write, I will write because see, function is defined for all x greater than 0. So what I have done, I have defined for all x less than 0 function as f of minus x. This is referred to as the even continuation of the function. Just definition, don't worry. There's just, you have to remember, this is referred to as even continuation of the function. And if I define my auxiliary function for all x less than 0 as simply minus of f of minus of x, this is called as an odd continuation. Okay, so now what will happen? Initially, your function was defined on only half interval, that is x greater than 0. This particular extensions, that is even or odd, may give us a freedom of extending the definition from minus infinity to plus infinity, and thereby executing our, you can say, Fourier sine transform or Fourier cosine transform. Okay, so let us say I want to expand a Fourier cosine transform. Okay, so if I want to expand a Fourier cosine transform, I would use an even continuation. I would use an even continuation of the function. And if I want to find a Fourier sine transform, I would use an odd continuation of the function, because you see, function is only defined for half on the half of the interval, only half of the interval, and you'll see that you'll get the similar formula as we've got in the you can say sine, Fourier sine and cosine. Just give me a little bit of time and you'll be able to understand what I'm trying to say. So for example, if my function f of x is simply this e to the power minus px, and let's say it is defined for all x greater than 0 and less than infinity, and here your p is greater than 0. So you can see that this particular function is only defined on the first quadrant, right? And if somebody says to you, find a Fourier cosine transform, so you know that if I have to define Fourier cosine transform, I would need that my function should be an even function. But here you can see that this is not an even function. You see, if I say that this is even or odd, you will say this is neither even nor odd, because if you replace x by minus x, so if I replace x by minus x, I will get e to the power px. Okay, so I'm just writing it here. So it is neither even nor odd. Now see, if I extend my functions, if I extend my function, you can say if I write an even continuation of the function. So let's say I'm defining my function now, a new function as e to the power minus px for all x greater than 0, and for all x less than 0 I'm defining it as e to the power px. So how would I make a graph of it? So the graph would be this way. Okay, and always remember that the even functions are always symmetric about y-axis. So they're always symmetric about y-axis, and you can see this also. You can see that. Okay, you can see that this is an even function clearly. And if you're not, if you think that this is really not the case, then you can see it analytically also. If you do f of minus x, what you will get? You will get simply e to the power px. If x is less than 0, that is minus x greater than 0 would give you x less than 0, and it will give you e to the power minus px. Here you will get x greater than 0. This is equal to f of x clearly. So f of minus x, you will get f of x. So you have to remember that initially when I was saying that find the Fourier cosine transform of e to the power minus px, so you would say how would I do it? Because see, e to the power minus px is neither even nor odd. So what is the suggestion? The suggestion is write write a continuation of this particular function. So if I am saying that e to the power minus px is defined for all x greater than 0, I will actually write an even continuation to this by simply replacing the definition for all x less than 0 as f of minus of x. And you can see that clearly this is an even function. Now if you have an even function and you know that the Fourier transform of an even function would yield you a Fourier cosine transform. Okay, since this is an even function, now you can clearly write here Fourier cosine transform, and I have written that Fourier cosine transform. The formula is given by GCK is simply root over 2 upon pi from 0 to infinity and you have this, I think, fc. This particular function, you write it by some other name, let's say capital F here, so that at least there is some difference. Okay, otherwise, okay, so fcx into cos kx, and you have then dx. And another, if you want to write what would be fcx, it will be simply root over 2 upon pi, and then from 0 to infinity you will get gck and then I think you should have cos kx written here, and then dk written over here. Okay, I hope it is clear now. Okay, and now if you want to replace this definition here, so you'll get this particular thing, that what would be gck, because for all x greater than 0 it is simply e to the power minus px, so I will simply write gck is simply writing writing it as 0 to 2 pi, and then it is 0 to 2 pi, sorry, root over 2 upon pi, 0 to infinity, and then you will have e to the power minus px here, and then you have this cos kx here, and you have dx here. Okay, and this is simply what this particular integral, you can say this can be told as your Laplace transform of cos kx. Okay, simply I wanted to find, so I think this is quite easy to find the Laplace transform of cos kx. This is something that we have already learned in our previous sections, so one can easily write the Laplace transform of this. I know the Laplace transform would be simply equals to 1 upon p square plus k square. Okay, so this would be it. So I think this integration would be equals to, I think p upon p square plus k square. Okay, s upon s square plus a square hota hai na, so p upon p square plus k square, and then root over 2 upon pi would follow. The same question is, somebody would have asked you, what is this Fourier sine transform? So now, in order to write the Fourier sine transform of e to the power minus px, you have to go for an odd continuation. So if one wants to find what would be the what would be the Fourier sine transform for this particular function, then one would want to write actually an odd continuation of this particular function. An odd continuation of this particular function would want me to actually write the definition as this way. So I would have to write my definition f of x as simply e to the power minus px for all x greater than 0, and minus of e to the power px for all x less than 0. So what would happen? So this is how it is. Okay, this is how it is. And if I am writing e to the power px, so had I made a graph of e to the power px for all x less than 0, then this would have been the graph. I'm making in dotted sense, don't worry. Okay, I'm making in dotted sense means मतलब मैं तुम्हें बताने की कोशिश कर रहा हूँ कि e to the power px, the graph of e to the power px would be this way, but I don't want to make the graph of e to the power px. I want to make a graph of minus e to the power px. So basically I have to take a reflection over here. So this is how it would be. Okay, so this is the odd extension of e to the power minus px, and if I'm writing the odd extension, then you can clearly see that this is an odd function. If you want to see that, you can do that as well. You can just write f of minus x, and this you will get e to the power px here for all x less than 0, and for all x greater than 0 you will get minus e to the power minus px. Just take a negative common out, and you will find that this is equals to minus of f of x. So clearly you can see that this particular function is an odd function now, and if you have this odd function, then you can clearly define the Fourier sine transform. And what would be Fourier sine transform? This would be root over 2 pi integration from 0 to infinity e to the power minus px, and then this will be sine of kx dx. Clearly this is equivalent to writing the Laplace transform of sine kx, and the Laplace transform of sine kx is simply k upon p square plus k square. I hope it is clear. So one has to see, well, ये चीजें probably these are not going to be asked directly in the examination, but one has to see that you can actually write, you can actually extend the function, and then you can also write the appropriate Fourier cosine transform or Fourier sine transform depending upon what sort of continuations you are making. So for example, if you are making an odd continuation, then you will get a Fourier sine transform. If you are making an even continuation, then you will get a Fourier cosine transform. Okay, so now let us go further and do a few more things. Okay, so we were actually heading for the summarizing of this particular lecture. So let us go ahead. Okay, so now let us do one question, and then we'll move further. Let us try to find the Fourier transform of a finite wave tree. Okay, this is very standard. You'll find these treatment in Arft and Weber as well. So I'm just doing it from there only. So let us try to find Fourier transform of a finite wave tree. So let us try to find the Fourier transform of a finite wave tree. Okay, okay, okay. So just give me a minute, and I'll join you in a few minutes. Okay, Fourier transform of a finite wave tree. Sorry for the interruption. So let us discuss Fourier transform of the finite wave train. Okay. Okay. So I write the functional form here. So the function is given by f of t is simply given by sine of omega naught t if modulus of t is less than n pi upon omega naught, and if modulus of t is greater than n pi upon omega naught, then it is simply 0. Okay, then it is simply 0. So this is the you can say infinite wave train. Okay, like you can say sine omega naught t. So basically it is clipped uh, to a finite wave train having n cycles. Okay, so there are n cycles. So beyond t modulus t greater than n pi upon omega naught, the function is simply defined as 0, and for all mod t less than n pi upon omega naught, it is defined as sine of omega naught t. Okay, so this is one thing. And if I want to find what is the Fourier transform, so see, as I've discussed, sine is an odd function. So if sine is an odd function, so what would happen? Only odd term would survive. That is, sine term would survive. The cosine term in the e ki power iota kx or iota kt would not survive. Okay. So if you want to really write it, I'll write it for you. So if I want to find the Fourier transform of the finite wave train, it will be simply f of t into e ki power minus iota. If it is omega naught is given, I'll write omega t then, so that there is no such discrepancy as such. So this will be the Fourier transform of this particular function f of t, which is referred to as finite wave train. Okay. And if you see, this is modulus of t less than n pi upon omega naught. And if I write 1 upon root 2 pi also here, so I know that my function f of t is an odd function. Odd function for all mod t less than n pi upon omega naught. So for my all modulus of t less than n pi upon omega naught, I know that my function is odd function. So basically this particular Fourier transform would reduce to a Fourier sine transform from 0 to, instead of infinity, I would write n pi upon omega naught only. Why I would write n pi upon omega naught? Because see, if I write 0 to infinity, I know from n pi upon omega naught to infinity, this is simply 0. So the limits will only go from 0 to n pi upon omega naught. The other integral, that is from n pi upon omega naught to infinity, the function itself is 0. So there will be no contribution to the integral. So I'll simply write sine omega naught t here, and I will, instead of, I'll write here sine omega t dt. Okay. Okay. And by the formula, I know so if I write 2 here and divide by 2, so 2 sine A sine B, I know it is sine A plus B plus sine A minus B. So basically this will reduce to, I will directly write 1 upon root 2 pi. Sorry, 2 sine A sine B, the formula would be, I think, cos formula. Sorry. 2 sine A sine B would be, I think, cos of A minus B minus of cos of A plus B divided by 2. Or you can say, if 2 is written here, so it will balance itself. So basically what will happen, if you integrate it, then you will get simply sine of omega naught minus omega divided by 2 times omega naught minus omega. Lower limit t is equal to 0, so this will go to 0 only, because see, sine cos when integrated will give you sine. Okay, and if you place the lower limit, sine 0 is 0, so I'll only place the upper limit here. So I'll have this upper limit n pi upon omega naught minus sine of omega naught plus omega, and then you have this n pi upon omega naught divided by omega naught plus omega. Okay, and so so this is how your Fourier transform behave like. So this is how your Fourier transform would behave like. Okay, so this is how your Fourier transform would behave like. So one can clearly see that this particular Fourier transform, if I want to go for the let's say frequencies which are close to omega naught, frequencies which are close to omega naught, what will happen that this particular first term would only be very significantly large compared to this term. So as omega tends to omega naught, this particular first term would be very large. You can say that this would be the more significant term than the other one. Okay, so in the limit omega tends to omega naught, or you can say in the close vicinity to omega naught, you will find that this particular term will have a larger sort of contribution. Okay, and what I would generalize, I would actually discuss this particular Fourier transform in the limit omega around omega naught. So basically what will happen if this is the case, then only this so I can write that for omega close to omega naught, what I can say about the what I could say about the you can say graph of the function. So one needs to see where does the function become zero. So one needs to see where does my function become zero, because sine function is very easy to you can plot sine very easily. So where uh, where are the zeros of f tilde omega? So where are the zeros of f tilde omega? So basically what will happen, the zeros of f tilde omega will come at the place where omega naught minus omega divided by omega naught becomes zero. Because see, this particular term, if it becomes zero, then I know that my this particular term would be zero only. So basically this thing will have a what you can say, this thing will have a zero at all these places, that is omega naught minus omega upon omega naught whenever it becomes zero. So and it will, that I can say that this is simply the deviation of omega from the omega naught that I'm referring to as omega, delta omega divided by omega naught. And it will be possible only if you see this particular thing is zero. Okay, this particular thing is zero, or you can say uh, I would say sine of sorry sine of omega naught minus omega times omega naught times this n pi also, sorry, should be equal to what? Zero. Okay, should be equal to what? Zero. If it is equal to zero, only then this particular first term would become zero. Understand what I'm doing is I'm trying to find some relevant solutions only if omega is close to omega naught. So if omega is close to omega naught, only then I'm discussing this particular Fourier transform. Otherwise, this generalized result would follow. So for example, in exam, if someone asks what is the Fourier transform of the function which is represented as a finite wave train, your answer should be this. But if someone asks you what about omega close to omega naught? What about the frequencies where omega is close to omega naught? Then I will have, and if someone asks you the graph for the same, then I'm making the graph. Okay, then I'm making the graph. So basically, the first thing that comes to mind whenever you are drawing sine function, one thing that you need to see that where your sine function becomes zero. So your sine function would become zero when omega naught minus omega divided by omega naught times n pi should be equal to zero, or delta omega upon omega naught is simply, I think, you can say uh, uh, some multiples of pi. So I'll write some multiples of pi. I'll write some okay. So basically, what I want to justify, just give me a minute. Just see what I want to justify. That you see, if I'm writing if omega naught minus omega divided by omega naught, okay, if it is equals to what I want to say, if it is equal to, let's say, plus minus of 1 upon some integer, let's say n only if I take. So let us take n equal to 1. Let us take n equal to 1. So if n is equal to 1, this would be 1, this would be 1. And if omega naught minus omega divided by omega naught is simply 1, this would be 1 into pi, sine pi is 0. Okay, now take n equals to 2. So if I take n equals to 2, then omega naught minus omega divided by omega naught is 1 upon 2. and then you have this 2 pi. So 2 gets cancelled, you have only pi. Sine pi is again 0. So basically, if omega naught minus omega upon omega naught is simply plus minus 1 upon n, or you can say plus minus k upon n in general. Okay, so where k is belongs to natural number. So it may that this may also so happen. So for example, what I want to convey is that, see, you know that sine theta is equal to 0 if theta is equal to k pi. So basically I will write omega naught minus omega divided by omega naught times n pi if it becomes equal to k pi. Okay, if it becomes equal to k pi, or if I write that omega naught minus omega divided by omega naught is simply k upon capital N. Here k is also integer, n is here I think some integer or something that I took, I think. Okay, n is simply cycle, so basically it is going to be it is going to be positive, but you know that sine pi is also 0, sine minus pi is also 0, so this will take both plus and minus sign. So basically this is how I have written. Okay, so so how to make the graph for the same. Okay, so what are we discussing? Again, I'm reiterating, please do remember this is an important concept. It may be asked in your examination. Okay, so don't think that it is like, for example, one has to see that I'm discussing Fourier transform of a finite wave train. For a finite wave train, ft is given by sine omega t mod t less than n pi upon omega naught. So basically what I have done, I have clipped my sine function at some time. Okay, so I have clipped my sine function at some time. So basically and beyond that particular time, you can say beyond that particular period, you can say my sine the function is simply 0. I have already stated that whenever your function is an odd function, you know that your function will be your Fourier transform of the function will reduce to the Fourier sine transform, and sine transform goes from 0 to infinity. But remember, from 0 to n pi upon omega naught, your function is fine, this is sine omega naught t, but beyond n pi upon omega naught till infinity, this is simply 0, so this is not going to yield you anything. So this will be the final integration that you need to evaluate. What I have done, I've used the formula of 2 sine a sine b as cos a minus b minus cos of a plus b. Simply here I have written it, and then I'm trying to plot this particular graph. In order to plot a graph which contains sine, one has to remember what? One has to remember that what are the zeros of the sign, because otherwise you know the pattern of sine. So why I'm doing this? So for example, if one asks what is the graph of the function, then it will be very useful for you. Okay, then it will be very useful for you, and you will find the graph is actually similar to that of amplitude curve for the single diffraction pattern. So basically you'll find, I'll draw the graph, don't worry. And this I am making this particular graph is of the function f tilde omega, that is Fourier transform of f in the limit omega close to omega naught. So in the limit omega closer to omega naught, I am making the graph of the function. Okay, now see what will be the value at almost tending to omega naught. So basically exactly at omega naught your function will not be defined, so you need to take the limit of it. So limit omega tends to omega naught, sine of omega naught minus omega divided by omega naught into n pi divided by 2 omega naught minus omega, and then there is some, I think, root over 2 pi also is given, so I'll write root over 2 pi also given. Okay, and since here you have 2, so what I'll do, since here I have 2, so what I'll do, I cannot write 2 here, so I'll take this 2 outside only, so that okay, this is one thing, and I have to multiply by n pi upon omega naught, so I will have to here multiply by omega naught upon, acha, this is on the denominator side now. So if I if this is on the denominator side, n pi upon omega naught, so I'll write omega naught upon n pi. This will again become n pi upon omega naught, so it will become again n pi upon omega naught. In the limit omega tends to omega naught, this particular limit will become 1. this particular limit will become 1. So basically what will happen about omega tends to omega naught, the function, that is the Fourier transform, will actually show an amplitude, which is simply 1 upon root 2 pi, 1 upon root 2 pi, and then you will have this n pi upon omega naught. Okay, so this is how your amplitude will be as omega tends to omega naught. And then you have this function of sine only, no? So basically how does sine behave? Sine will start decreasing. Now problem with this particular function is, you see, I'm just trying to show you. Okay, so if you see that this particular function, if I write in this particular form, that is the form here. So from here, if you see this particular form, so you know that the amplitude of the function is actually dependent upon the number of cycle. That is one thing one needs to see. And the zeros of the function, so you see the zeros of the function are what? So I'm just going to write it here. So you see, I'm writing delta omega upon omega naught. It is equals to what? It is equals to plus minus 1 upon n. Okay, so what will happen as n grows larger, the width, that is delta omega, that is omega naught minus omega, would start decreasing. Okay, this is one thing that you should remember. Second thing, you will see that if you try to trace the graph of the function, what will happen? So I'm writing it here. Okay, how should I write? Just give me a minute. I'll write it slightly at some place so that you're able to understand what I want to convey. Okay, so don't forget what is the problem statement. So problem statement lies the same. Basically, we are trying to make the graph of sine of omega naught minus omega, and here you have this, I think, n pi upon omega naught divided by 2 times omega naught minus omega. This is the graph that I'm trying to make. So if you see, the amplitude will also contain this term. So basically what I can do is, just give me a minute. So if I just take it here, okay, if I just take it in the amplitude side, okay, one thing what I want to convey is this. Let's forget about it. Okay, and remaining terms in the you can also see that this amplitude also depend upon the number of cycles. So basically where your wave train is clipped, that is also important. Okay, but right now I'm just writing the general pattern. So this pattern would be like 1 upon root over 2 pi, and then you have simply n pi divided by omega naught. This is constant, this is n, this is the number of cycles. So basically this will be, I think, some constant only, so forget about it. But again, you see the amplitude itself contains the term omega. So your amplitude, I will write A for amplitude. A, that is the amplitude, is also a function of omega. Okay, so if omega grows large, this will go towards 0. So if omega is large, this will go towards 0. And secondly, also understand, as n tends to infinity, this delta omega will also go towards 0. So these are all the hints that I'm giving to you. They may be asked in your examination, directly or indirectly. Okay, right now for the sake of the graph, I'm making the graph. So you see that as I go along, the first thing is clear, that if I increase my omega, my amplitude will start decreasing. So what will happen? The graph will be like this. My amplitude will start decreasing, and as I go all along, as omega goes towards infinity, my amplitude will start dying out. Okay, similarly here you see the graph will be symmetrical, but you see as omega grows larger, your amplitude will start dying out. So basically this is the graph of your f tilde omega, or you can say this is a graph of your Fourier transform of the finite wave train, and it is actually resembling the graph of something that you see in your optics. That is, if I correctly remember, this represents your amplitude curve for the amplitude curve for the single diffraction experiment, okay, or you can say single diffraction pattern. You see, single slit diffraction pattern. This is something that you see in your standard 12th also, okay. Okay, so this is the amplitude curve for the single slit diffraction experiment. So if someone asks you what is the Fourier transform of this finite wave train, so if I make a finite wave train, how it would be? So this is how it is, the finite wave train. Basically, it is simply a sine function. And what is happening if you are actually making a Fourier transform this particular function? This is actually going and becoming like this. So this will actually resemble an amplitude curve for the single slit diffraction pattern. Okay, and if you remember this particular format, you might have seen that this is also one of the representations of a Dirac delta function. If you see, this is one of the representations of your Dirac delta function. If you just go back to my lectures, and if you see that when I was discussing with you the representations of Dirac delta function, one of the representations of the Dirac delta function was this particular function itself. So it resembles in another way uh, uh, as one of the representations of Dirac delta function. So if someone asks, how do you think that your Fourier transform of a finite wave train would behave? Your answer should be it will resemble to an amplitude curve of a single slit diffraction pattern, or it may resemble to some of it may also be, you can say, represented as a Dirac delta function in the limiting case. If you remember, I have done it for you, I think. Uh, because exactly at omega equals to omega naught, this will not be defined. So basically, uh, as large as you can take, like as large as n, if you take as large as possible. So if you take n as large as possible, this will try to squeeze when these amplitudes will try to move towards the origin only. So basically, as n are increased, that is, if n tends to infinity, what will happen? As n tends to infinity, in the limit omega tends to omega naught, this will be actually an infinite narrow spike about omega equal to omega naught, and overall for all other omega naught, for all other omega not equals to omega naught, there would be something very close to zero. So basically, this will represent this is one of the representations of Dirac delta function as well. Okay, so basically this is sort of, you can say that this is kind of central maxima. Okay, so this is central maxima. So most of the contribution is coming from the central maxima, and beyond central maxima you will not have a uh, you'll not have a contribution. So basically, if n is made larger, then outside the central maxima, you will not have much of the contribution. So I hope I'm able to make sense. If you really feel that there is some difficulty that you're not able to understand, kindly let me know in the comment section. Okay. Now another thing that I wanted to convey is okay. Basically, this is the last turn today. Okay, so then I will actually shift to a new topic so that we also get some kind of encouragement. Okay. Okay. So another thing that we have done quite many times, but let us take one question and then we'll go ahead so that you'll have some sort of motivation again, because I feel the motivation is lagging in this particular topic. I don't know why, but this is somehow, I would say that this is an important topic. This you will find that in exam, not much questions are asked in Laplace transform, but more questions are asked in Fourier transform. Okay, so let us do one question from exam itself, so at least you get some sort of inspiration. Okay, some sort of inspiration. So basically, this is the question. I'll give you 2 minutes to think about it, and then I'll do it for you. So this is how your function is behaving. I'm just making the graph. So you'll find that in exam, the peaks were located at x equal to some plus minus like 1 by 2, then 3 by 2. I'll write it, don't worry. This is 1 here, this is 2 here, this is 3 here, this is 4 here, so on and so forth. And similarly, you will have a graph here as well. minus 1 here, minus 2 here, minus 3, so on and so forth. Okay, so you know that these spikes are located at, I'm writing the spikes are located at t is equal to 1 upon 2, 2n minus 1. T is equal to 1 upon 2, 2n minus 1. So here are, you have these spikes, and these spikes you can actually write it as some Dirac delta function only. So basically you can have these basically what is happening, that at these Dirac spikes you have this infinite narrow spikes. Basically this can be written as some Dirac delta functions of strength plus minus 1, of strength plus minus 1. What would be the amplitudes in the Fourier expansion? So what will be the amplitude? You can write Cn in the complex Fourier expansion. Okay, so this was a question that was asked in your exam only. Okay, so this was asked in, I think, net exam 2015 somewhere. Okay, so this was the question. So how to write the Fourier expansion? So one knows that whenever there is a sort of periodic function, so you can see that what do you think that the period of function would be? The first thing that comes to our mind, that what would be the period of the function? So you clearly see that this pattern is getting repeated here. So what is it? It is, I think, 3 by 2 here. What is the point here? This is minus 1 by 2. So clearly this particular pattern, you can say to you can see that this repetition of the pattern takes place with the period t is equal to 2. Okay, so if you take this particular term, so this will be, I think, plus 1 over half, sorry, plus 1 by 2, and here you know that this will be, I think, minus 3 by 2. So clearly you can see that this particular pattern, that is the negative spike pattern, is also getting repeated at period t equal to 2, and the positive spike pattern is also getting repeated at t is equal to 2. So clearly the period of the function is t equals to 2. Is that clear? I hope this is clear to you. Okay, now you see, if I want to write and I know that I have done this particular derivation also for you, that if your function fx is periodic, if your function fx is periodic, and if I want to write a Fourier exponential series, so how it is written? It is written as n equals to minus infinity to n equals to plus infinity, and then I can write Cn, then e की power iota 2n pi x, or because here t is given, so I'll write 2n pi t divided by capital T, where capital T is the period of the function, where capital T is the period of the function. So I'll use ft then, sorry, instead of fx. So this is how you write your this is how you write your complex Fourier expansion of periodic functions. And I know that my periodic function, this particular periodic function, has the period t. So basically the what is happening, that t, capital T, that is the period of the function, is simply 2 here. Okay, simply 2 here, sorry. So the period of the function t is simply 2. So how would my Cn would behave? My question is, how would my Cn would behave? Now this is, I'm leaving to you as a, just take 2 minutes for this, and then I'm going to start with the question. So if you remember, if I want to find the Cn, the Cn's are written as minus t by 2 to plus t by 2. If you remember, the Cn is equal to minus t by 2 to plus t by 2, and then you have this f of t, and then you have, I think, e की power of minus of iota 2 n pi t upon capital T dt. So this is how you write your Cn. This is how you write your Cn. Okay. Now you see, if I want to write my f of t, if I want to write my f of t, what do you think your f of t would be? So basically, what is happening? F of t is having Dirac delta is somehow represented as a Dirac delta function. So basically, at t equal to minus half, you have a minus a Dirac delta function with a negative strength. At t equals to 3 by 2, you have this Dirac delta function of a positive strength 1. At t equals to 5 by 2, you again have this minus. So basically, what is happening? Alternatively, the function is having a spiky kind of behavior. So alternatively, you have this Dirac delta function. Okay, alternatively, you have a Dirac delta function with alternate signs also. So one has to see how to write the expression itself. So basically, what I'll do, I'll actually reduce it to um, I'll use this t equal to capital 2 so that things would become easy for me. So basically what I'll do, I'll write Cn is equal to minus 1 to plus 1 because t is equal to 2, so t by 2 would be minus 1 to t by 2 would give you minus 1 to plus 1. And here I will simply write f of t. Don't worry, I'll write f of t later on, but just write f of t as of now. And then you have this e to the power of minus of iota, and then you have this n pi t, and this is dt. Okay, because capital T is 2, so 2 gets cancelled with 2, so you have this n pi t dt. Okay, now you see from minus 1 to plus 1, you see from minus 1 to plus 1, oh, what is happening? Just give me a minute. Okay, so if you see from minus 1 to plus 1, minus 1 to plus 1, there are only two spikes. One spike is at Dirac delta, one spike resembling a Dirac delta function is at t equals to minus half, and another spike at t equal to half is of negative strength. So what I'll do, I'll write the definition this way. So from minus 1 to plus 1, okay, so from the t lying from minus 1 to plus 1, okay, if t lies between minus 1 to plus 1, your f of t, I can write it as Dirac delta function t minus of minus half, that is t plus half. So at t equal to minus half, you know that the strength of function is 1, and at t equal to half, your strength of function is minus 1. So at t equal to half, your strength of function is minus 1. So this is how you can write your ft. So now your Cn would simply be integration from minus 1 to plus 1. This is Dirac delta function t plus half minus Dirac delta function t minus half, and then if I multiply this by e to the power minus iota n pi t dt. This is how I'm going to do. So now you know from the filtering property of the Dirac delta function that we have done in the previous lessons. I'm just going to remind you because a few people have joined. So basically from minus infinity to plus infinity, if I want to integrate f of x and I have this Dirac delta function x minus x naught, then this is something referred to as the filtering property. This gives you the value of the function at x naught. So basically what you need to see is where your Dirac delta function is stationed. So your Dirac delta function is at x equal to x naught. So basically what does it mean? At x equal to x naught, you will have a narrow infinite spike. And if I integrate from minus infinity to plus infinity, f of x into Dirac of x minus x naught dx, this will give me f of x naught. So basically what will happen if I do this particular integration, the first integration if I do, what I will get, I will simply get e to the power of iota, and then I will get n pi upon 2, basically at t equals to minus half. If I use t equal to, basically what does it mean? It means t is equal to minus half. So basically the Dirac delta function is located at t equals to minus half. So basically t equal to minus half will be replaced here. So at t you will get a minus half. So I have simply written minus half here. So this will be iota n pi upon 2, and then minus of e to the power of iota, I think minus iota n pi upon 2. Okay, so this is how you're going to write. Now if because in the examination it was solved further, so if I solve it further, what will I get? So just give me a minute, I will write it for you. Okay, so the Cn, if I just divide it by 2 iota and 2 iota, if I multiply, okay, there is something missing, I guess. I think 1 by 2 is missing. No, sorry. Okay, my mistake. So basically whenever we write this f of t na, cn, so you get 1 upon t also here, otherwise this will be a wrong thing to do. Okay, so remember that cn is written from minus t by 2 to plus t by 2 integration ft e ki power minus iota 2n pi t upon capital T dt, and this 1 upon t also comes, okay, because you have to integrate dt from minus t by 2 to plus t by 2 also. So basically 1 upon t I forgot to write, so I'll write 1 upon 2 here as well. I will write 1 upon 2 here as well. Okay, so what will happen? Your Cn, simply I have to write 1 upon 2 here. So if I've written 2 here, I will simply multiply with iota and I will divide by iota. Okay, so I'll get simply iota, and this is sine of n pi upon 2. So answer, I think this was the answer, iota into sine of n pi upon 2. This was only the answer in the exam. I hope it is clear. So this is how you do your questions in the exam. Okay, so I hope we have done quite amount of questions for your for this Fourier transform. A few of the topics are left. I think we'll be able to cover it one day, but probably from tomorrow we'll start with a new topic. Okay, so I hope to meet you tomorrow with a newer topic, and until then, take care.